In this video, we are going to use partitions, upper sums, and lower sums to prove these two properties for the Riemann integral. Let me give you a moment just to read through them, then I will come back and name them, and then we will work through their proofs. The context here is imagine that we have two functions f and g, which are nice bounded functions on the bounded subset A of Rn. Each is scalar valued, and we know each to individually be integrable. So f and g are nice integrable functions. The first property tells us that if f is less than or equal to g, so you can imagine the graphs of these functions, f sits below g, then the integral behaves in a way that you would anticipate. That is, that the integral of f over a is less than or equal to the integral of g over a. This property here that, we preserve this relationship between f and g when we take their integrals over a, this is monotonicity. And then the second property tells us that if you form a linear combination out of the functions f and g, so any scalars b and c used to create a new function of the form b times f plus c times g, this is what we call a linear combination in mathematics. This itself is integrable. It might feel obvious, especially if you've done lots of integrals, but that needs to be shown. So we need to prove that this linear combination of integrable functions is itself integrable. And the integral of this linear combination is a linear combination of the integrals. So again, this behaves exactly as you would expect. We break up the integration across addition. We can pull out scalars, but we will prove that. And this property, of course, as I've alluded to with my language, is called linearity. These two proofs are similar. We'll start with the first one because we don't have, extra scalars and it's a little bit faster, but they will follow the same train of thought, which is that we will think about how f and g for this first one, how they behave over subrectangles for any partition. That will allow us to conclude information about, say, their lower sums, lower integral, etc. And then same thing for linearity. We will compare upper and lower sums of this new function, the linear combination of f and g, to upper and lower sums for the original functions. Let's start with this proof of monotonicity. We already know that f and g are integrable functions over a, so I know that both sides of this inequality exist. I just need to show that the inequality is correct. To do that, let's first start with just a random partition of any rectangle S in Rn, which encloses the domain A in the usual way. So I'll start by saying proof. Let S in Rn, just trying to think how I want to phrase this, be an in rectangle. And when I say that, I mean with nice sides parallel to the coordinate axes, enclosing A. Now let's chop up S using any partition P. So let P be a random partition of S into a family of subrectangles, which we can denote as S sub I. It's a finite collection. So you could even be more precise than I usually am by saying into capital N subrectangles S sub I. Okay. F and G are defined on A. They are not necessarily defined on every point in S because we've extended the domain, but when we defined the Riemann integral for this context, we just said set the functions to be 0 on any point in S which is not in the original domain A. So since F and G are both defined to be 0 outside of A, this inequality that F is less than or equal to G is still preserved. And in particular, when I look at F and G over each subrectangle, the infimum of F must be less than or equal to the infimum of G. I'm going to need this notation a few times, so let me bring in a notation for infimum of F over the subrectangle named S sub I, and likewise for G. So let little m sub I of F and little m sub I of G denote the infima of F and G respectively, over S sub I. Okay. So if we have capital N subrectangles in our partition, then we have capital N infima for F, one for each subrectangle, and likewise for G. So we would index these as M1 of F all the way through M capital N of F, and likewise M1 of G through M subcapital N of G. All that to set up that this number for each subrectangle has to be less than or equal to this number, because if they weren't, if that inequality wasn't preserved, you actually could show that this isn't necessarily true. I don't think I want to get into that because it's about how infima for functions work. So let me state it, but you can pause and take a moment to work out that the following statement is true. Since f is less than or equal to g on S, the infima for F is less than or equal to the infima for G for each subrectangle SI. Okay. On my piece of paper, all of this takes up like one line at the top. I didn't really expect to fill the full board with just this setup, but I'm going to step aside now and let you make sure that you have all this down. And then when I come back in just a moment, I'm going to erase everything and we're just going to do like one large inequality computation based on this observation. So we will be able to take this observation about their infima and conclude that the same inequality must be true about their lower sums with respect to this partition, and therefore their lower integrals with respect to all possible partitions. And then since they are integrable, the lower integrals are exactly this. So that's really just the entire proof done out loud, but I will come back in just a moment and write it down formally. Now that we have observed how the infima of these two functions relate to each other over any possible subrectangle of any possible partition, we can start talking about their lower sums. So notice the lower sum of f with respect to the partition that we were just looking at is computed as the sum over all subrectangles created by the partition of the product, the infimum of f over each subrectangle. Sorry, not using my notation. M sub I refers to the subrectangle, and this is the infimum of F times the volume of the ith subrectangle. I am just choosing to use this notation that means add up over all of the subrectangles created by the partition. It is a finite sum. And since we said that for this particular partition, there were capital N members, capital N subrectangles, what you could do is say I equals 1 through capital N if you wish to. So if you want to write this down a little bit differently, what is important now is that we go up in size with the observation that we just made. So this infimum of F over the ith subrectangle is less than or equal to the infimum of G over the same subrectangle times the same subrectangle volume. But now, of course, we recognize that this is exactly the lower sum of G with respect to the same partition. Okay, so take any partition of a nice rectangle S enclosing the domain A, and what you find, and it's not surprising given the hypothesis that we're building this result off of, the lower sum of F with respect to any partition is less than or equal to the lower sum of G with respect to the same partition. Now, if we imagine all possible partitions and formed both of the lower sums for all of these partitions, this would form a set of lower sums, this would form a set of lower sums, and what we could say is that the sup of this set of lower sums is less than or equal to the sup of that one. Let me just go ahead and write that down. Therefore, the sup of all possible lower sums of F with respect to all possible partitions P of S is less than or equal to the same construction but for G. But what are these two measurements? This is exactly what we call the lower integral of F over A, and this is exactly what we call the lower integral of G. F and G are both known to be Riemann integrable. So when we say lower integral, that is, in fact, just the integral. So let me see if I can do both of those conclusions on the same line. Thus, the integral of f over a, which because f is known to be Riemann integrable, is equal to the lower integral of f over a, and that is exactly this set supremum, is less than or equal to the lower integral of g over a dv. But g is also integrable, so when we say lower integral, we could just say integral. Those two numbers exist and they are the same quantity. All right, that wraps up this one. And again, it's not surprising because f sits below g. So when you think about all possible estimates that you could make, say if you're doing some sort of volume computation, you would expect to enclose less positive volume here than here. So it's going to preserve the direction of the inequality. Okay, when we come back in just a moment, we will look at the linearity result. As I alluded to in the opening, this proof is going to be a little bit longer. Part of the reason why this proof is more complicated is that we don't actually know right away that this linear combination is itself integrable. So in the previous exercise, everything was integrable. We were just showing that an inequality was satisfied. Here we have to also get integrability as well as this equality. We will end up doing a proof by cases to cover the different signs for B and C. So it's like we'll have B and C both be non-negative, then we'll look at probably not positive and maybe one positive, one negative. The first one is going to be the heart of the argument in terms of partitions, and then the others are kind of like algebraic manipulations. I want to give you just a warm-up exercise first before we jump into that. We will need to compare expressions of the form m sub I of, let me just write f plus g, forget about scalars for a moment. So think about the supremum of the two functions f plus g added together over some ith subrectangle. That quantity versus adding up their infima separately. I think I might have said suprema a second ago, but basically this is an infimum for the function f plus g over the ith subrectangle. Here's the sum of two infima, one for f, one for g, over the same subrectangle. How did these two terms compare? So the infima of the sum versus the sum of the infima. Take a moment to work out what the answer is. I'm not going to do a full proof. I'm just going to give you a sketch so that you can remember how these relate to each other, and then we will start with the proof where we assume that b and c are not negative. It's tempting to throw an equality between these two expressions, but it's an inequality. And let me give you the reason in words, and then I'll sketch a picture. This is the infima for f anywhere in the subrectangle. This is the infima for g anywhere in the subrectangle. If you think of it as just like a minimum, it's like you can pick an x for f, you could pick an x for g. You're allowed to pick different points, so you can really like go small with both of these terms with different inputs. Here, it's like I can't pick different inputs for f and g. We are adding them together, forming a new function, and then saying what's the infima of that over the same domain. So it's like you might not land on the small values that you had over here. I just did that kind of casually in words. Of course, they might not be minima, they might not be single variable functions, but for a nice example with single variable functions, consider, say one of these is 1 minus x and the other one is x. Okay, so let's say f of x equals x. And g of x is 1 minus x. And here I'm just looking over the unit interval from 0 to 1. On the right-hand side, when I add these two functions together, it's the constant 1. So over here, I would get 1. But over here, I'm allowed to move around in the domain and pick different, places to look for both of these infima values. Over here, it's 0 for f, whereas over here, it's 0 for g. It's 0 on the right. Okay, so I just wanted to mention that because I've seen people just throw equality in here, like you can distribute this idea of an infimum and you cannot. We will see this in just a moment when we start this proof by assuming that B and C are both positive, or rather non-negative. The start of our proof is almost exactly the same as the previous one, so I've done it here quickly and concisely. Just like in the previous exercise, let P be any partition of a nice enclosing rectangle S enclosing the domain A into a finite collection of subrectangles, which we will call S sub I. For this particular case, suppose that the scalars B and C are greater than or equal to 0. Then, going to see how much we can fit on this board. It's just going to be a long computation with some inequalities. I'm going to start with B times the lower sum of F with respect to this partition plus C times the lower sum of G with respect to this partition. Let's now say what that is in terms of a summation. So that's going to be the scalar B times adding up over the subrectangles in the partition, the infimum of F over each subrectangle times the volume of that subrectangle, and then same thing for the second term. Okay, these are finite sums. What I'm going to do is not write down the intermediary step, but as a first step, imagine just pulling B and C inside of the summation so that I would have B times the infimum of F for this first one. Here's what's a little bit dangerous. Again, there are a couple places where you have to be careful with your algebra, like that inequality that we just worked through. A random scalar times an infimum is not necessarily equal to the infimum of the scalar pulled in. So what I'm about to write down, you have to be careful. If B were negative, your function actually flips. Sups become infs and vice versa. But if B is greater than or equal to 0, I can pull this B into the summation and then into this infimum computation. So that's what I've done from here to here. And then same thing, we're just going to assume C is nice as well. So let's bring C inside and then inside. These are two finite sums adding up over the exact same subrectangles. So again, I'm not going to write the intermediate step, which is to say the sum of these two sums would be the sum of this plus that. Notice that BF and CG are two separate functions now whose infimums we are computing over each subrectangle. I'm going to go up in size by bringing these together and using the lemma that we just established. So again, you could basically erase the second summation and view this whole thing as one big sum. And I'm going to take these two infimum computations and merge them into one that looks like the infima of the sum, the linear combination of F and G. And by the discussion that we just had with x and 1 minus x, there's an inequality here. We go up in size because here, these infimums can happen kind of differently over each subrectangle. But here, I'm assessing these two functions glued together with this linear combination over the same domain. So I can't move around individually inside of this linear combination. Okay, not to belabor the point, we now have this expression. Let me pause, see if you can write down the next thing that I'm about to write down. Make sure that you can digest everything so far. What's coming next? What I wanted you to recognize is that this sum where I've left off is exactly what we would write down if we wanted to do the lower sum of the linear combination, the new function that we're studying, with respect to the partition P. So let me go ahead and squeeze it here. So this is the lower sum of BF plus CG with respect to the same partition. I want to say one more thing before I have to erase everything. To continue the inequality, because I actually have more lines that I want to write down. I'm just out of room. This lower sum exists because BF plus CG is bounded. F and G are both bounded. B and C are scalars. This linear combination is bounded. And one thing that I really tried to emphasize when we studied how to set up Riemann integration is that as long as your function is a bounded function, lower sums with respect to any partition exist. So this number exists. And the upper sum of this linear combination with respect to the same partition also exists. and those two numbers satisfy this inequality. So this lower sum for this function, which we still don't know is Riemann integrable, but what I'm saying is it has a lower sum with respect to this partition, and that lower sum is less than or equal to this upper sum. And that's where I'm going to hesitate for just a moment so that I can erase this and we can continue. But what I would like for you to do is try to finish the computation on your own for a few moments. I did all this kind of work gluing these quantities together to get to a lower sum. Now we've gone up in size to an upper sum. See if you can kind of like take this upper sum and sort of reverse this process. So the idea now is we're going to unglue all of this into expressions which kind of take us back to something that looks more like how we started. Okay, so undo this is what I want you to try to do so that we can start to prove this result for positive or non-negative scalars B and C. Here's where I left off. We haven't done any upper sums in this video yet, but we know what this would look like. It would be the sum over the same subrectangles as before. I'm going to use capital M sub I to denote the supremum of this function, BF plus CG, and then times the volume of each subrectangle. Now, I wanted to give you a minute to get to this point and realize that you need to break the supremum up. And just like before with infimums, it's not equality, it's inequality. And of course, it's like if you could pick different parts of the domain for each of these functions individually, you could try to make both of them really big at the same time. But when you glue them together, you're much more constrained. So we are going to go up in size when we break them apart. That explanation I do is not a proof. Of course, that's just like how I like to think about it. So here I don't have any ability to evaluate these two pieces on different parts of the domain, but when I break them apart, I can. So we go up in size to M I B F, sorry, the supremum of the function B times F times this volume. Let me go ahead and split this into two sums because once again, I'm almost out of room, but I think you see where we are going. CG. Now the B pulls out, so we can take this B, pull it in front because B is non-negative. Again, you have to be careful if the scalar is negative, you can't just pull them in and out of sups and infs. But let's pull it in front and in fact here. And same thing, C, I could pull it here and actually here. And now that I've done that, we recognize that this is equal to B times the upper sum of F with respect to the given partition plus C times the upper sum of F with respect, G, with respect to the same partition. And this is true for any partition. So we still have the key pieces of information here, which is this quantity is a lower bound for this quantity and this quantity. So I've got the lower and upper sums of the function we are trying to assess squeezed between this quantity and this quantity. Okay, so it's really these four pieces that I've underlined that we need to think about. Remember that F and G are known to be Riemann integrable already, which means I already know, if I start looking at sups of all lower sums, what this would look like and what this would look like. And then we have these two pieces squeezed in the middle. So that's going to allow us to finish the proof for this case in just a moment. But let me pause, erase, come back. We'll wrap up this situation, and then we will discuss what to do with potentially negative scalars. Here's what we left off with. Let's focus on these left two terms first. We have a comparison between a linear combination of lower sums and the lower sum of a linear combination. This inequality holds for any partition P, so when we take the supremum of possible left-hand side values and possible right-hand side values, we will preserve that inequality. And in particular, what we'll get over here is going to look like B times the lower sum over A of F, the integral of F over A, plus C times the lower integral over A of G. That will be less than or equal to the lower integral of BF plus CG over A. Now, this lower integral exists whether or not this integrand is Riemann integrable, and also we know that it will be less than or equal to the upper integral of BF plus CG over A. And that's actually what we would get here if we took the infimum of all of these upper sums compared to the infimum of our combinations over here, and we'll get that this is less than or equal to B times the upper integral over A of F plus C times the upper integral over A of G. Now the thing is, F and G are Riemann integrable, so everywhere I wrote lower integral for F and lower integral for G, it's not necessary. Same thing with the upper integrals because their lower and upper integrals are the same and they are the integral of the functions. Therefore, the function of interest, BF plus CG, its lower and upper sums are squeezed between the exact same number. So they actually have to also be that same number. So let me just write that over here. I think we're ready to finish this problem. I'll just kind of imply it over here. These two numbers are the same. They're equal to each other. Didn't give myself enough room, but that's okay. And what is this shared value? It's these bounds on the end, and those bounds are b times the integral of f over a plus c times the integral over a of g, just like we wanted to say. Okay, so that takes care of this linearity proof. In the situation where these constants b and c are not negative, the reason why I've separated that out, and I'm now going to think about negative scalars as a separate computation, is because when you talk about sups and infs, if you multiply by a scalar, you don't necessarily preserve the same notions. I will spell that out in just a moment. Let me step away so that you can wrap up this particular case. Then we will return and finish this problem. To handle negative scalars, what we will first show is that negative f is integrable if f is integrable, and the integral of negative f is -1 times the integral of f, exactly like you would expect. This result isn't really a separate result because it rolls into the original one where, say, b is -1 and c is 0. With the same notation as before, where A, the domain, has been enclosed in a nice rectangle and P is any partition of it, let's just jump right into an upper sum of this new function negative f with respect to this random partition. In the usual way, what we will do is add up over all of the subrectangles defined by the partition the supremum over the relevant subrectangle of negative f times the volume of the subrectangle. Okay, so we compute this for each of the subrectangles and add them all up. Now I want to pull the scalar -1 out front, but when you take a function and you change it by -1, you flip highs to lows and lows to high. So when I pull this -1 out here and ultimately in front of the entire summation, what was a supremum is going to now become an infimum. So that's just why I wanted to do this separately and not try to do the entire result all at once. Okay, but now what is this? This is exactly the lower sum of the original function with respect to the partition times -1. I'm not going to do the analogous computation for the lower sum. It's the exact same thing. We'll flip an infimum to a supremum. So you're welcome to show this on your own. The lower sum of negative f with respect to the same partition will be equal to -1 times the upper sum of the original function with respect to the partition. Again, exact same idea, except an infimum will flip to a supremum. Okay, so now let's try to bound the integral that we're studying between the integrals that we know. So what I mean by that is I'm going to start by saying about -1 times the integral over over a of f. Okay, so I know that this exists, and I'm just multiplying it in front by -1. This is equal to -1 times, I'm going to do full detail here. How about the lower integral of f? Okay, but what is that? That is -1 times lower integral. It's the supremum of all lower sums of f with respect to every partition. I'm going to omit the phrasing for all partitions P of S enclosing A. Same idea. I'm going to bring this negative inside, flipping the sup to an inf. Let me go one more time to the right. Inf of negative L of F P over all partitions P. But now I actually recognize that this is on the board. It's here. Taking the infimum of this quantity over all partitions P is the same thing as taking the infimum of this quantity. So I'm sorry, I'm just trying not to erase the board. I'm going to drop down here and kind of keep going to the right. This isn't how I like to see math formatted, but I'm going to run out of room. So same infimum. I'm just doing a substitution in here. This is going to get replaced with this. Infimums of upper sums give you upper integrals. So here, the infimum of this set of upper sums with respect to all possible partitions is exactly the upper integral over a of this function, negative f. We know that exists because negative f is bounded, so the existence of this is not in question. And we also know that it is greater than or equal to the lower integral of the same function. So that's always true for bounded functions over nice bounded domains, like A. Okay, so I'm going to keep going to the right and then down. How would I have gotten this? I would have said, well, let's take the supremum of all lower sums of this function, lower sums of that function with respect to all partitions. Do we see that on the board? We do. It's here. So the sup of these terms is the same thing as the sup of these terms. So I'm going to keep going down here. So same set supremum of the same set. I'm just going to write it differently as this. Okay. And let's pull that negative outside, flip it to an inf. Okay, we're almost there. -1 times an infimum of a bunch of upper sums. This is going to give us the upper integral of f over a, and then times -1. But f is integrable, so that's actually just -1 times the integral of f over a. And I'm not going to write any more. I'm going to say we're done with this exercise. Let me highlight the key moments. Up here, we have negative integral of f, and then we have lower integral, upper integral, and lower integral right here. Okay, there we go. Of the function whose integrability we are trying to assess. So this is the key idea. Are these two things equal? Well, they're squeezed between that quantity and itself. So that these four pieces here are the key to concluding integrability for negative f. These two pieces are squeezed between the same number, so they are equal to each other and they are equal to this number. So I'm just going to say that out loud. We have now shown this result, telling us that if f is integrable, negative f is integrable, and its integral is -1 times the integral of the original function f. Okay, that gives us a nice way to handle negative scalars. I will finish the story with that situation in just a moment. You can now consider, what if one of the scalars was negative? What if the other one was negative? Let me just handle the case where they're both negative. You'll see immediately what to do in the other two cases. So we can wrap this up pretty quickly. If I have B and C negative, and I'm looking at this linear combination, what I can do is just say that is the absolute value of B times the function negative f plus the absolute value of C times the function negative g. We just proved that if f and g are integrable, then so are negative f and negative g, and we know what their integrals are. And now by taking the absolute value of the scalars, these are non-negative. So we've reverted back to that very first situation that we addressed. We know this is integrable right away, and we can say that the integral in this situation is going to be, okay, so let's just pull the scalars out front. I'll do this in 2 steps. You can do it in 1, but let me just do it like this. Like so. But now negative f, negative g, we know how to handle those. Just pull the negative out front. And as we do, we will be able to go back to the original scalars as they were written first. So it is negative absolute value b. It's whatever b was. And we're done. Let's not make a mistake at the very end. Finished. Okay. So that finishes, with maybe 2 cases that you can nail down, but it's very similar to these. That finishes the story for having scalars which are not necessarily negative. And again, I wanted to highlight there that you need to be careful with sups and infs when you do things like pull scalars out front. Don't be too casual with that kind of operation because there are some considerations that you need to take into account. Okay, that wraps up this look at proving 2 familiar properties about Riemann integrals using partitions.